So in today's video, I'm gonna be implementing linear regression from scratch using only NumPy and NumPy only as part of my journey to learn machine learning. And it won't be like some simple linear regression, nah, it's gonna be a full-on multiple linear regression with ordinary least squares, gradient descent, and all the inference for the coefficients and model evaluation. So let's get started. If you want the follow-on implementation code and the Jupyter notebook, plus some math derivation notes for linear regression, check out the GitHub repository I made in the description. So yeah, before implementing the linear regression, we gotta know the theory. And behind the theory, there is the math. These are the math topics you should have a good grasp on before diving in. The stuff like matrix operations, multivariate calculus, statistical inference, and probability theory. Before the core implementation, we need some data to test our model on. Just a simple function to generate some dummy data, which will allow us to know the true values of the coefficients and the true responses, which will be so useful later when we evaluate our model performance. Phase 1 is going to be about the core implementation. This is the matrix form for multiple linear regression. It will be very helpful when dealing with multiple predictors and large data sets. So yeah, better get used to it. The first real step in any machine learning algorithm, including linear regression, is to estimate the parameters. In this case, those are beta coefficients. They tell us how much each predictor contributes to the output. Think of them as the link between the response and the observation. There are two primary methods to estimate these coefficients. The first one is ordinary least squares. This is a classic approach. Works well with small to medium-sized datasets. And the most important thing about it is analytical, meaning we get the solution in one shot using a closed form formula derived from minimizing the residual sum of squares. And this is the formula. You just plug in the X matrix, you calculate, and boom, you get your coefficients. Before discussing the gradient descent, which is the second method, let's introduce the concept of the loss function, which is simply just the difference between the predicted response value and the actual value. In the linear regression case, the mean squared error is the loss function. So yeah, we call the gradient descent. This is an iterative algorithm. It's better suited for large data sets when calculating the inverse in the closed form is too expensive to deal with. It gradually tweaks the values of beta to minimize the mean squared error. So our goal is to estimate the coefficients to minimize the mean squared error. Gradient descent doesn't give you the solution instantly. It searches for it step by step based on the gradient of the loss function, which is just partially derived vector from the mean squared error. Now to the code. Here is the implementation for the OLS, just calculating the transpose and the gram matrix, which is just the X matrix multiplied by its transpose. Plug them into the formula and boom, you get the predicted coefficients beta hat. And here is the gradient descent approach. As you can see, it loops with a set number of iterations with two hyperparameters, the alpha, which is how big the step we take each time, and the batch size, which is how much data we use to learn where to go. Think of it as someone lost in a foggy mountain, using the informations and the terrain he can see to indicate the way down to the mountain. Translating this into an algorithm, the person is the gradient descent algorithm, and going down is minimizing the coefficients, and the info gathering is the batch size. The algorithm steps goes like this. We initialize the coefficients to 0, and now we loop till our coefficient is converged, aka minimize the mean squared error the best it can. Okay, inside the loop we compute the gradient vector for the loss function. After it, we calculate the new coefficients and we update it, and we check if it converged or not. If it did, we break out the loop and return the estimated coefficients. As you can see, they both estimate the same values, which means that both the OLS and the gradient descent works well. So yeah, we're chilling. To finish the first phase, let's quickly code the mean squared error function, which is just the square residual and divided by the number of observations. And yeah, also this is the prediction function. As the name implies, it predicts the responses given X predictor and beta hat that we just estimated right now. So yeah, that's the linear regression. At its core, it's simple. You estimate this and predict that and you're done. But some of us are overthinkers and they be like, who says that my estimates are correct? And also that my predictions are right? Phase 2 is gonna be about statistical inference. Here, we're gonna assess and see how accurate our estimated coefficients beta hats are, using some nerdy methods. The first one is the standard error. It's just the squared variance of the estimated coefficients, aka the standard deviation of our estimated value, aka how much our estimated coefficient will deviate from the true values. Here is the implementation. The function takes on the mean squared error and the gram function as arguments, and calculate the beta hat variance and the standard error following this simple formula. And plugging in the values, return the healthy values, which says that the error in our estimations aren't that big, and yeah, we're cool. But you know, some people just want to be confident on their estimations, maybe 95% confident. That's why after calculating the estimated error, we can now construct a confidence interval. And the good news that we are 95% sure about that interval. Using the t-table from 95% confident, we can calculate the upper and the lower bound using this formula and stack it with numpy to result in this interval, which is 95% again confident that the values of beta should fall into these intervals. Pretty cool, right? And the last method, which can be both used to model evaluate and statistical inference for the coefficients, is the f-test, also known as the f-statistic. Using the concept that you should already know, hypothesis testing, here is the null hypothesis. It says there is no relationship between the response you're getting and the observations you have. I won't call this a liar, nor I will believe it, so we will perform the f-test, which calculate the original variance and the noise in the raw data before we fit, which called the TSS. Also calculate the variance we have after we fitted the model, which is the RSS. We plug them into the f-test formula and get the f-score, which after looking up in the f-table looks pretty good and healthy. And now we can call our null hypothesis a big liar. So yeah, after all this overthinking and testing, there is only one thing left to do, is to evaluate how well our model does and fit, aka the quality of fit. There is mainly two methods that can be used, the residual standard error and the R-squared, given by these simple formulas that both uses the RSS and the TSS we calculated earlier. I prefer the R-squared because it's proportional and gives a simple metric. The closer to 1 indicates that our model fits well and performs well. The closer to 0 means a poor fit and we probably messed up the estimation, or the data just doesn't fit. Sometimes you can't fit a relationship between x and y. That's what she said, unfortunately. Anyway, linear regression is simple. Estimate some coefficients, predict stuff, check if you are on the right track with statistical inference, and if you are worried, construct some confidence interval, test the hypothesis, and check the R-squared, and you are good to go. And if you want more details, theory, math, derivations, check the special GitHub repository I made, or check the video that I made to explain the linear regression. Thank you for watching.